This is actually a project I've been battling on with Kenneth and Dieter and a couple of other persons. Mark is not here, I think. Björn is also not here, but I think you know pretty much all of those persons. And we're examining the distribution of giant invertebrates in the Palaeozoic, based actually on a finding which was made by Kenneth some years ago. When he was doing fieldwork in Morocco, he found this big specimen. This scale bar is actually 5 centimeters. It's an orthocone, an actinocerid. And you see this is the last chamber which is preserved. It has a diameter of 27 centimeters. And we calculated the length of the complete shell, which is pretty much perfectly cone-shaped. And then we come to a length of about 3 meters or so. And that's quite impressive for the early Devonian. We know larger orthocones from the Ordovician. I have depicted a reconstruction here. This is my girlfriend swimming below them. And actually, I have made I've reconstructed two sizes. This one is based on this specimen here, which is on display in the Smithsonian. But there's also a written report of a specimen which has been found in a quarry near New York and which has been broken and used to produce gravel, so it doesn't exist anymore, and there's also no photograph of it, but according to this report, there would be 10-meter long Ordovician endocerids that roamed the seas in the Ordovician. But this we cannot test, this extremely large size, but this one is testable based on this specimen here, because if we reconstruct that, and most of it is actually septate, so I think this is possible that actually this is all still fragmocones, or the body chamber is still missing, and then we wind up at a size of about 6 meters or so. Yeah? Okay, and there's some other giants from the Palaeozoic, there's 2 big genera in the Devonian, large climenids and large manticoceratids, and this is the famous large Echolopterus from the early Devonian. And this is the Ogygenus, the so far currently largest known trilobite with almost 1 meter in length. And this is actually this species here, this actinocerid from the early Devonian of Morocco. So just to depict this shortly, so among the trilobites, you have especially large forms in the Ordovician. You know, this is Ogygenus from Portugal, and this is Isothelus rex from Canada. And then, of course, I don't know, Peter's here. This is from his work on the Anomalocaridids from Morocco, from the Ordovician. And I think he found an even bigger one, which will be published in the near future, I hope. Probably also in another Nature paper, I presume, if I know Peter well enough. And so this will be also like 1.5, 2 meters long or so. I don't know what the complete size would be. And of course, in the Ordovician, we have these large endocerids, and they're actually not so rare. And then if you look at the Devonian, this actually slipped back anyway, so there should be Devonian here. There's also big forms in the early Devonian. That's actually why I actually got into studying the distribution of invertebrate gigantism in the Palaeozoic. And we found more of these large actinocerids. You see, here's a specimen, where actually shell length of 2 meters is preserved. We're going to dig this out probably next year. And then there's Echolopterus. Here's the Hele of the Heliceers here. And then there's also nice large trilobites. This is, of course, a reconstruction. And this might be a Moroccan reconstruction. But they do get big, but they're actually never articulated. You always find isolated sclerites, but that's what they looked like, this Scabrella. I think it's not completely false, but it might be assembled from various specimens. And then, of course, we have large orthocones all throughout not throughout the entire Palaeozoic, but from the Ordovician to the Carboniferous. And this is one of the famous large Rhinoceros specimens from Arkansas. I think this is Walter Menger, if I'm not mistaken here. And there's in the Silurian of Morocco, we have also really large orthocones. And this is Silurian here of Gotland, and another, well, this actually doesn't belong here. It's an endocerid, so this belongs to the Ordovician slide, basically. Okay, so we came up with a couple of hypotheses we wanted to test with our little study here. And we were wondering if there's a distinct pattern, if there's times where there's more giants or times with less giants, or where they grew bigger or not so big. This is the first hypothesis. And then we're wondering, are they equally distributed over space? Because you all are aware that actually today there's this polar gigantism where we have large forms near the poles in the high latitudes. Would this apply also to Paleozoic forms or not? And then we asked ourselves, what could drive or enable giant growth throughout the Paleozoic? So of course the first question is, what is actually a giant? And of course you cannot come up with an absolute definition there. It's always a bit arbitrary. And we defined it like this. We looked at the largest specimen we could find in the literature or ourselves in the field. And then everything which is minimum half the size or larger than the largest specimen we included in giants. And it sounds like there should be a whole lot of forms included there, but actually it's not that much. Yeah? So it works quite well. It serves our purposes. We don't get a terribly large sample. It's actually quite small sample, which we obtained like this. And of course, we should not have, it should not be a very everyday size we obtain like this, obviously. Yeah. Okay, then the interval we looked at was the time between 500 and 300 million years, both from the Ordovician to the Carboniferous. And the groups we examined were these ones here, so ammonoids and the forms with straight shells, and then Eurypterids, because we had nice data we could take from a paper from James Lambsdale, and trilobites, they were done by Mark, because he also had a database available already, so we could rely on that. And anomalocaridids, of course, since there's not so many species, we could not use that quantitatively, but we just looked, okay, how were they distributed in terms of geography and also in time. So this is the first graphs we produced. On this side, you have the diversity, and this would be actually the size, the maximum body size you obtain for each stage. And you have the time scale here, 500 million years, 300 million years. And the red stars mark giants, and the curve itself is just the maximum size we have found. But of course, there's a whole bunch of biases and noises in there, obviously, because, for instance, in orthocones, I'm sure we have not checked every paper that published on some kind of orthocone somewhere in literature. So we missed certainly something here and there. So it's really impossible to get all the data there. For ammonoids, I think the data are quite good, but you see that actually the size data are quite uniform. So we have really large, well, reasonably large forms throughout the middle and late Paleozoic. And then for the Eurypterids, we could also, of course, not include all Eurypterids, because there are some Eurypterids which are freshwater or even terrestrial, so we could not include them. So we took also only a part of the Eurypterids are included here. And there's 3 forms which grew to really impressive sizes, exceeding 2 meters, as most of you know. And then for the trilobites, there's a bunch of really large forms in the Ordovician, as I mentioned before, and also in the Devonian and the Cambrian, of course, too, as well. So coming back to my hypotheses from before, are there distinct patterns? It's not really obvious. So there's not one single time or stage or so where there's more giants than otherwise. So it's not a very simple pattern or straightforward pattern we can observe there. Then the question for ecological factors, we compared these occurrences with the diversities over time. So we have in, I think, what was it? Yeah. Green is sample and bin, so it's just simple taxon counts. In most cases, it's genera and species is here, genera here, and families here. And the red curve is a subsampled curve based on the mean standing diversity. So what you see, there's a way correlation between diversity here and the maximum size of the forms we found in the respective time unit. So there's some correlation between size and diversity. Okay, so the question is there a random spatial distribution, or do they like polar latitudes, or did they like it warm or whatever? And if they are not randomly distributed, what were the possible drivers, ecological drivers, favoring large growth? So do you have polar gigantism? Is it temperature-driven? What ecological parameters did play a role enabling the formation of giants through time? So polar gigantism, if you look at these maps, starting here in the Cambrian to the Permian, well, there is some forms which are in really reasonably high latitudes here and here, but then if the further you go in the younger parts of the Palaeozoic, the more they wind up almost in low latitudes. They're not really equatorial maybe, but there's not a, well, at least for the Palaeozoic invertebrates, we can reject the polar gigantism hypothesis. So is it simply temperature driven? I think that's also not true, because you see they're quite widely distributed. You have them sometimes, you have them in warm areas, sometimes in moderate climates, so there's also not a simple correlation there. But what we do see is that here in the early and middle Palaeozoic, they seem to like the middle latitudes actually. So there's no clear correlation, but they seem to favor certain regions, so to say. And then there's the link between upwelling and nutrient supply. The more darkly shaded areas here, these are areas where we suggested that there could be upwelling, and you see also they don't care if there's upwelling or not. They're wherever they want. I mean, there's no obvious link there. So random spatial distribution, that's the question. If not random with drivers, yeah. And then the next thing we examined if there's a correlation with latitudinal diversity shifts. And this is something we submitted this paper a couple of times, and one of the time it was rejected, but we got some really interesting comments, and this put us in the right direction, I would say. So we looked at the latitudinal distribution over time of the single groups. And if you look at all these at our 4 groups, you can actually see that from the time from 500 to 400 something million years, they just shift back and forth in latitude. But thereafter, like in the middle to late Devonian, they actually start migrating towards lower latitudes. And the interesting thing is that all 4 groups do this independently. And then, well, that's how we submitted the manuscript at one point. And then one author actually did the effort. He took the PBDB data and to see what the diversity does. And we didn't think of it for some reason. And it turned out that actually the diversity does the same. So we have the diversity peaks that also shift simultaneously in the same directions. And so we do have a uniform latitudinal shift in the body size, if you want, the maximum body size, which starts actually in the late Devonian, which is, might be linked with these macroecological changes which have occurred at that time, the changes in climate and so forth. And what's also interesting, if you look at the atmospheric oxygen, it does more or less the same thing. So it's more or less stable until 350 million years or so, and then you have an increase in oxygen. So this correlates quite well. This suggests there might be a link here. And we suggest that the late Devonian to early Permian cooling and atmospheric oxygen increase might have been linked somehow, or might have favored, or might have shifted the gigantism latitudinally. And so, maybe it's the marine oxygen that might have favored this or controlled this shift. And in any case, we have a parallel displacement, latitudinal displacement of maximum body size and marine diversity, which of course is something you would expect, that in the place where you have the highest diversity, you would get the largest forms as well. So in that respect, actually the Paleozoic giants are normal giants. They do what one would expect. So where you have the highest diversity, you might get the highest disparity and also the largest range in body size. And I think this is more or less it. And I just want to repeat my invitation for next year's meeting. If you have forgot or if you weren't there yesterday, there's no excuse now. If you're working on cephalopods, please come and visit us next year for this meeting also. And thanks for your attention.